So hello again. Tonight we're going to talk about a star that is a bit more than a white dwarf, but a bit less than a neutron star or a pulsar. And we'll discuss all the details of it and the implications for us, given the fact that it's headed our way. Not anytime soon, certainly not in our next few thousand years, but given the amount of radiation it might be putting out, we might want to be concerned about it for a while before it actually approaches us. As to what do we do? So I've started using NASA Night Sky Network imagery. This is the life cycle of stars poster. You can always get a PDF and then get a JPEG and put that in your presentation to show things off. And if you look down towards the bottom, you'll see that the end result of the end-of-life degeneration of stars can be, if you're small, not as big, not as energetic, become a white dwarf. If you're bigger, you become a red supergiant, and then you go supernova, and then you either become a neutron star or a black hole. And a neutron star, as it spins high speed, spitting out radiation, it's also known as a pulsar. The white dwarf is not supposed to be rotating fast or spitting out radiation, but the neutron star is expected to be devoid of higher order matter and have converted all the atoms into neutrons through a process involving electrons. So I think of this observation of this white dwarf as it's just another point on the curve of the degeneration of stars at the end of their life. So as I said, larger ones go supernova, neutron stars, black holes. Smaller ones produce planetary nebulae and form white dwarfs. What we're finding out as we see more and more stars is there may be some between the points where it's bigger than a neutron star, but less than a black hole. And so maybe that's what this white dwarf is. And I've even included the recent speculation by more than just yours truly regarding quark stars or strange stars. But we're going to take a look specifically at one stellar remnant. It is a white dwarf. That's what the WD stands for. That's its catalog identifier, 0812-3529. Rolls trippingly off the tongue. There's two different kinds of white dwarfs that we've seen. One is singular or non-binary pair, and those will tend to produce electromagnetic radiation in the UV through infrared range. And strangely enough, the first time we've ever observed a singular white dwarf was in 1917, because they're very small and very dim. And we observed it in visible light. We typically capture white dwarfs in mid-infrared survey observations. So we're taking pictures of big swaths of the sky at certain levels of exposure. And if we look at that over time, we'll see that, the star is not kind of glowing like a regular star, and it's whitish in color, shows up in infrared at a certain wavelength, and they do spectroscopic analysis on it, and they see, oh, look, I don't see any hydrogen. Must have run out of fuel. So it must be a white dwarf. The other kind of white dwarfs we see are in binary pairs, where you have one of the two stars being a red supergiant and the other star already having run out of its fuel and is now a white dwarf, and its gravity is sucking material off of the red supergiant on to form an accretion plate around the white dwarf. And when that builds up to a certain level, it'll detonate on the surface of the white dwarf, possibly blowing up both stars, or possibly just blowing up the red supergiant and not the white dwarf, or possibly compressing the white dwarf into a neutron star. So this is the two kinds of white dwarfs we see. It's atypical to observe a white dwarf in radio bands longer than deep infrared. To see what kind of emissions there are gives us a clue as to kind of the age and the amount of matter that's in that star. We did in 2016 find AR Scorpii, which is in Scorpius, and it emits in X-ray through radio and its rotation, its spin rate is 3.56 hours. So it rotates very slowly, which says when it shrunk down to a white dwarf as a star, it was moving very much even slower. The old, spinning ice skater approach of if your arms are way out when you start spinning and then you bring your arms in, you'll spin faster. So in order for this very large white dwarf to be spinning no faster than 3.56 hours, that says when it was really a big star, it was spinning real slowly. The spin rate, or the pulse period in the case of pulsars, is related to how far you decrease in diameter from when you were a star to make you spin faster. Also, this AR Scorpii is believed to be spinning down because it has a giant magnetic field around it. Typically, the white dwarfs that aren't part of a pair, they're not as energetic, and so you won't find as sizable a magnetic field around them. So here's the target of tonight's presentation. So if anybody wanted to get all the data currently known about this beastie, it's a singular star. It's not part of a pairing, not part of a binary. It's also in a catalog of UPM as J0812-3529. Again, rolls trippingly off the tongue. But,
that one. Yeah, that one.
Yeah, that one. But where they found it originally was in a survey at the infrared level in the 2-mass survey, and it has a huge catalog identifier. The J says basically Julian 2000, and then the 2 dashed coordinates are the right ascension and declination to find it. So in the 2-mass catalog, there are so many stars that they just don't worry about giving them a name, don't worry about giving them a Greek letter within a constellation. They just give them the RA and DEC coordinates of where they saw it last. So a white dwarf is what's left after a smaller star fuses all of its primary fuel and it shrinks down. This particular white dwarf is in our galaxy. It's in the constellation of Puppis, the ship's keel. And it is viewable from South Florida in October for a while. It doesn't get that far above the southern horizon. There's a space probe at Lagrange Point 2 from the European Space Agency. That probe is known as Gaia, and it has a huge catalog of data. And it was first included in data release number 3. So you might also see it with a really long, just raw catalog number of Gaia DR3 and then that long series of digits. That's just a catalog identifier. If you're looking at it spectroscopically, it's DAH, which says it's the white dwarf. I don't know what the DAH stands for, but that's white dwarf classification. Its last measured distance, using parallax, is 36 light years away from Earth. Its age, by its spectroscopic and metallicity analysis, is about 2.7 billion years old. So it actually died out before the age of our sun. But we're seeing it from 36 years ago. Its mass is about 0.63 of the sun. And I've got some numbers there to compare it against, the sun's mass versus the mass of the Earth. So it's a fraction of the sun's mass. The radius of this white dwarf is 0.01 or 1/100th the radius of the sun. And you can see that would make it 6,950 kilometers in radius, and the Earth is 6,378 kilometers. So it's a bit larger than the Earth, but nowhere near the size of the sun. It's a white dwarf, so it's not that bright. It's magnitude 14.5 or thereabouts, which means you're not going to see it naked eye, and you're not going to see it even through a small telescope. Here's the first oddball thing that they discovered is it has a 30 million Gauss magnetic field, or 3,000 Tesla. Your average MRI machine is about 1 Tesla. This thing is more than 3 Tesla. So this thing is 1,000 times stronger magnetic field than a contemporary MRI machine. This could literally move the hemoglobin in your blood around by the magnetic field. The radial velocity, this is kind of like us watching it, how fast it's moving towards us, is difficult because it's moving towards us, so it's not red shifted, it's blue shifted. And we haven't looked at a lot of those. We've looked at a lot of the supermassive black holes in the center of galaxies. Part of it is moving away, part of it is moving towards us. So that's the experience we have at measuring things that are blue shifted. There's not a lot of stars heading towards us, so we don't see a lot of blue shifted. So the first time we did observations in infrared, we forgot to take into account the fact that it was blue shifted. So we came away with an incorrect number on its velocity moving towards us. The second thing is the intensity of the magnetic field bends things, and therefore the wavelength also gets bent by the intense magnetic field. So they did another study of it and came back and said, no, that one's wrong too. And when they calculated in both the blue shift and the high magnetic field, instead of it being 4,448 kilometers per second towards us, it's only about 80 kilometers per second towards us. And at 80 kilometers per second, it's going to take a lot of years before it'll get anywhere near us. It's not expected to hit the Earth or hit the sun or hit Jupiter or anything nasty like that. It's going to traverse the edge of the Oort cloud. So it's going to be, about 1.5 light years out from our sun, out at the outskirts of our solar system. And they're not expecting it to, disrupt any comets in the Oort cloud. So why would I even bring this up? What makes this worth talking about? It's not its diameter, not its mass, not its luminosity. It's your typical smallish white dwarf. Not even the radial velocity coming towards us, although that's something we need to get a handle on and understand and monitor over time. Not even the fact that it's arriving in our Oort cloud. It's going to be 1.5 light years away from Earth, so not worried about that. As it passes through the Oort cloud is very large. I think it's around 20 astronomical units in width. So it's very broad and not very dense. So as the saying goes, space be big, and it's not going to have a good probability of interacting with anything in the Oort cloud. Even if, think about it for a moment, this is a star and it got ejected from wherever it came from and it's heading towards us. If its gravitational field were large enough, it could be dragging with it an asteroid belt or a Mercury or something like that, a planet, as it's coming towards us. If we're talking about anything colliding, that disturbance of the field of debris or planets, that's got a higher likelihood of interacting with things just because of the sheer size of it than the actual white dwarf itself. They're saying that the pulse rate of this is very slow. The original star was moving slow enough that when this thing shrunk down to a white dwarf, its rotational period could be as slow as once a minute. The rotation period of our sun is about 24 days. So if our sun, at the end of its life, became a white dwarf, that 24 days would shrink down to a fraction of a second because the diameter reduction. But this thing started out apparently larger, and when it shrunk down, it only got down to the point where it's now spinning at 1 minute. So it must have been rotating very slowly when it was a star. But typically, we don't see pulsars or neutron stars spinning that slowly. They typically spin with a tiny fraction of a second rotation rate. So think of it as a slowly rotating lighthouse. It didn't shrink down to a neutron star, so it doesn't have that intense gravity in a small area, but it still has a lot of gravity, and it's still rotating and producing radiation. But we don't know what kind of radiation is the problem. Typical emissions from white dwarfs, you'll get soft X-ray at the high end, down through ultraviolet and into some visible. Some white dwarfs will actually get down to the microwave radio level, and that's the lowest energy, and that's actually below infrared. But the actual wavelength and the amount of photons, amount of photon density is not currently defined for this, because we're just starting to observe this as its own self white dwarf in a survey, that came from a survey. So if this thing is really rotating slowly, and as it gets to within several light years of Earth, that beam of radiation will be slowly sweeping our solar system. So it'll be interesting to know, how intense the beam is, how fast it's rotating, what its composition is, many, many years before it ever gets close enough to us for us to worry about its gravitational effect. Plus the fact that we already know that a neutron star, when it becomes a magnetar, it's because it has a very high magnetic field, and that can actually alter the emission content and force of the polar jets. So if this white dwarf has an excessive magnetic field far beyond what we would normally expect from a white dwarf, that could add some oomph to its emissions. Now, I don't want to scare anybody because this thing is thousands of years away, but I'm more concerned about the emissions than it colliding with anything or, dragging comets from the Oort cloud. So we need to start taking it seriously to look at these things with all the instruments and all the different wavelengths that we have available to us. So from a gamma radiation perspective, we should have integral, Swift, and Fermi looking at it. From X-ray, we should look at the observation history of Chandra and current XMM Newton. Obviously, from ultraviolet, Hubble Space Telescope is good for that. But we could also have, in infrared, the James Webb Space Telescope. Take a look at it. Russia has their own radio telescope out at L2. It's called the Spectre RG. Plus, if it's producing emissions in radio bands, we could have ground-based radio telescopes like the Deep Space Network. Take a look at it. And if it's really strong enough in frequencies that'll make it all the way down to ground level, then we'd like to get amateur radio astronomers taking a look at it. Tomorrow is the monthly online session for the SARA, the Society of Amateur Radio Astronomers. And I'm going to ask them if anybody has any big radio dish telescope time available to maybe take a look at this in October, queue up a survey for it, because it's my understanding that not the largest radio telescope at Green Bank in West Virginia, but the next smaller one down isn't used as much and might have some free time on it. So I'll talk to them tomorrow. So the beam characteristics of a pulsar, and I'm describing this as, what if this thing is closer to being a emission characteristic pulsar than it is simply a white dwarf? So we're going to have an analogy of the beam differences and how the beam might be slightly different. So if you look at the two diagrams down at the bottom, a neutron star you can think of as an X-ray laser beam. Very narrow beam, sweeps very fast. So if it's close enough, if it's within, a light year of the Earth, the diameter of the beam by the time it makes it to the Earth may not even be the diameter of the Earth. So it might be like a very intense flashlight shining on a part of the Earth. If this thing is a wider energy beam and broadband, it's not narrow, it's more like an electromagnetic floodlight. And if the beam is wide enough, the beam width at the distance to the Earth could be larger than the diameter of the Earth. So the question is, what is the emission of this white dwarf, and how will that affect us as it arrives, during its pass, and after it departs? And will 1.5 light years distance in the Oort cloud be sufficient to protect us? We need more data, we need more wavelengths, and we need to monitor this thing over time. So here's some analysis. Some specifications on the Earth. We know the Earth rotates in 24 hours. We know its diameter. We know its circumference. Here's something to think about. What is the rotational sweep speed of the Earth? So when the Earth is rotating, how fast, if you had a point on the Earth, how fast is that point going around? And it turns out it's about 0.29 miles per second. So that's how fast it's going around. What is the orbital sweep speed? So if the Earth is going around the sun, how fast does it move through space? And it moves through space on average, because it's not a perfect circle, it's a slightly elliptical. So it's moving through space at about 18.5 miles per second. So if a beam were to sweep past the Earth is rotating and the Earth is also moving. What will be the sweep speed, the angle alignment, and the path direction of the white dwarf's beam versus the movement of the Earth? So let's first talk about the sweep speed. If the sweep speed is synchronized with the Earth orbital period, then that could be a bad day for us, because as the sweep starts to encounter us, we're moving in our orbit around the sun at pretty much the same speed. So if that sweep lasts for 24 hours, we now have the Earth being bathed by the beam, whatever the beam is producing. The not so bad news is if we did get a synchronized sweep like that, the odds on it coming by again next year is not as likely. So we might get one bad sweep out of it. What if the beam alignment angle, you think of the plane of the Earth around the sun and the tilt of our solar system, what about that tilt versus the tilt of the beam coming off of this white dwarf? The beam is essentially polar jets. They're coming out of the north and south pole of this white dwarf. If the white dwarf is vertical and we're vertical, then the beam will never interact with us, which would be great. If the beam is turned over on its side, then it could sweep across us and catch us that way. The beam angle versus the tilt of the Earth and the plane of the solar system is something that we need to make sure that we're not in a sweet spot to get a bad day. And what about the beam path direction? So the Earth is orbiting the sun counterclockwise. If this thing has a beam direction that's also counterclockwise, then there's a higher probability of us sweeping together. If the beam is clockwise and we're counterclockwise, it's like ships passing in the night. There's a lower probability of the beam being on us for any significant period of time. If it were a really bad day, and if this thing produced infrared, visible, it should be UV, not UR, ultraviolet and X-ray, and things were to line up where we got a full 24-hour dose around the surface of the Earth, that could be a bad day for the Earth and the living things on it, particularly if this thing has a high beam flux in X-ray to gamma. It could do nasty things to our atmosphere, particularly the ozone layer. But if the beam path is short and the beam flux is high and the bandwidth is in X-ray, our atmosphere would likely protect us, may not make much of an effect on our ozone if it's not too much gamma. So we might be able to take a few passes without getting adversely affected. But it would certainly be something you could detect. Let's say this thing was not quite at 90 degrees, but was at, let's say, 45 degrees where the beam didn't swipe past the Earth directly, but it did sweep the solar system. All of the stuff in the solar system would be illuminated by this radiation beam. So dust particles, asteroids in the asteroid belt, some planets that are have a very high albedo, like Venus, for example, planets that have radiation effects like Jupiter, a little bit of Saturn, those could be more brightly illuminated. So we might find that it could be a good light show for us, even if we didn't get hit by it. You think of the aurora, this could produce a solar system-wide aurora, depending upon what the beam output is and its angle and how we see it. It would be interesting to see that what we think of as the night sky particles, if you look at the zodiacal light in a dark site, imagine the zodiacal light being visible in the daytime. All depends upon the wavelength of the radiation and how intense it is. So this is always kind of my favorite way of measuring things. When a lot is less than a little. If you've examined radiation and its effects, we originally started out just looking at the energy of radiation exposure, and we found out that the exposure duration, or units per hour, really needs to be considered as part of the exposure. If you have a beam that goes past the Earth and it's very intense, but it sweeps past the Earth in a fraction of a second, and that's the last we see of it, it could be very, very intense, and it wouldn't produce that much effect because its dwell time, its rate against the Earth's atmosphere was not significantly long. But if this thing is lined up and synchronized and rotating slowly, even if it's far less powerful, the flux is a lot less, we could have a lot more exposure to the Earth. And the way I try and create an analogy of this is, imagine getting hit with a 2,000 watt blue light for a tiny fraction of a second every day for the rest of your life. So long as you weren't looking at it and you were wearing clothes, you not only survive, you probably wouldn't even get a sunburn from it. But compare that to getting hit with 500 watts of bright white light for 1/2 second every 2 seconds for the rest of your life. You might not immediately die from it, but you'd likely want to stay indoors for the rest of your life. And if you go outside, you probably want to wear some kind of protective suit, just because the accumulated exposure would not be healthy. So short-term and long-term effects. The Earth has a thick atmosphere. We have a UV protective ozone, and we have a magnetic field. So it really does protect us from solar radiation all the time. When a beam of intense cosmic rays, gamma rays, or X-rays strikes a planet's atmosphere, it can actually diminish or strip it away completely. So let's take it down a notch and say it's not going to be so intense, because it's going to be a 1.5 light years, that it will remove the atmosphere and all our water. If it's close enough, it's a high energy enough gamma ray burst close to us, it could do that kind of nasty, but let's say it's less than that. If the ozone layer were significantly depleted, it would indirectly expose the Earth to significant and long duration ultraviolet radiation from the sun. So the radiation that would be harmful to us wouldn't be coming from the white dwarf. It would be coming from the UV radiation after effect of this white dwarf pulsing and diminishing our ozone. UV actually exists even at night at high altitudes. And Helen and I saw this firsthand at Yellowstone National Park when my glasses, which go gray in the presence of ultraviolet, actually went gray at night. So we knew there was ultraviolet up there. So if the exposure is not too much and short-lived, it gives the Earth's atmosphere time to recover. And if you've read up on the history of the ozone hole, you can see that if we stop doing bad and we start paying attention, the Earth can actually start to recover its ozone layer and close up the hole. But if this thing is hitting us all the time, every so often, and the energy level is cumulatively just high enough, it won't have time to recover. So under heavy UV exposure for a long period of time, even plants would be okay for years, but eventually even plants would die out. Animals would die out from exposure much sooner. Even animals living underwater to maybe 100 feet or so below the surface, they would die out. Only life in deep caves or in the deepest parts of the oceans might survive under long-term exposure. The deep sea life would actually have a food source of the decaying things descending from above for a while. Higher order life in caves would probably exhaust their food source and die out. Not too long. Once the exposure ends, over time the ozone layer might recover, and then life in the deep oceans might once again come up on land and repopulate the planet. That's a worst case scenario. But we never know how bad it is going to be until we start taking more of a look at it. We want to know what's our jeopardy level. We're already doing that by looking at near Earth objects and asteroids and comets, and there are other things out there that go bump in the night, as the saying goes. They don't have to actually go bump. It could pass 1.5 light years away from us, and if it's lined up just properly and it emits at the right wavelengths and flux, we could have a bad day just about as bad or worse to an actual impact. So we need to start looking out for these other sorts of things that can affect us. So we need to confirm that it's on approach, how fast it is, and what path it's going to be, so where it will clip our solar system. We need to determine its magnetic field strength, and we need to determine the characteristics of the beam, how fast it's going around, the angle of rotation of the beam, versus the Earth's orbital angle, and then the sweep direction versus the sweep direction, the rotation direction, the sweep direction of the Earth in its orbit around the sun, and the diameter of the beam as it's approaching, how large it's going to wind up being, and then on its departure. Because if it's going to be a high energy beam, we might want to start monitoring it 5 light years out until it's 5 light years beyond. We need to see what bands it's going to emit in and how much energy it produces in those bands. So, in conclusion, the stellar degeneration curve probably has a few more points on it that we have yet to observe. And apparently this falls into, it's beyond a white dwarf, but not quite a neutron star. It's a slowly rotating, intensely broadband radiating an intense magnetic field. So new stellar types will show up in this degeneracy curve, and we need to do more observations on them. This thing was first reported as just your typical white dwarf until they started looking more at it. Burst velocity was not bad, and as we take into account things like the blue shift and the magnetic field, the speed changes. So don't just take one observation and think you've got a good beat on things. I would be less concerned about the direct or indirect dragging for debris collisions, that it might be dragging planets or asteroids or comets with it. I would be more concerned about the direct, continuous, and indirect electromagnetic radiation emissions. As our observing technology improves, so will our ability to see more of these things. We need to remove our blinders and start observing things in all capable wavelengths for all threat types, not just the things that are going to smack us, but the things that could radiate us. We need to reevaluate things because remember, in the last century, around the 1920s, we thought that Andromeda was a nebula, and then eventually we realized once we had a good image of it, hey, that thing's just like the Milky Way. I guess it's a galaxy. Oh, look, there's billions of them. So keep observing, keep improving the observational technology, and things will change. By the way, this is an artist rendering. They have not taken a picture of a neutron star. And then I have some links as usual. A couple of slides worth of links. Okay, so was there enough minutia regarding this particular white dwarf? I try and pack it full.
Yeah.
How many years was it before we realized we need to start looking out for the near Earth objects, the Earth orbit crossing objects, to see if they might be a threat? Then we found thousands of them. None of us are targeting us anytime soon, but we didn't know the potential until we started looking for them. And I think radiating stars that might be approaching us are things we need to look at as well.
So the nearest one would be in our far distant future, but is there anything at all that we could do to protect ourselves? I mean, it wouldn't help to just move to Mars, for instance, because it's going to be our whole solar system.
Yes.
Can we build a shield out of neutrinos, or is there anything that you can think of that we can do to protect ourselves?
Here's the concept. This thing is probably a few thousand years away, not the 100,000 or million years away, but probably a few thousand years away before its radiation emission might be something we want to take into account. At what point do you start researching the technology you're going to need to create defense for it? If it takes us 500 years to come up with an improvement to the Earth's magnetic field or some kind of external shield, force fields or whatever, how long does it take us to develop the technology for that? Well, we know that these emissions are electromagnetic radiation. I don't think we're going to send a nuke up and nuke the white dwarf, because the white dwarf would just swallow up a megaton warhead and go, thank you for the appetizer. So, yeah, I think we need to start first, do what we do with the other things that might impact us and say, let's examine the threat. And once we examine the threat, now we're doing things like sending impactors out to say, what are asteroids actually made of? And we found that, well, there are some that are hard, rock, metal kind of things. But a lot of that stuff seems to be loose gravel balls that if we hit it with something, it just kind of like splashes out and then gravity pulls it right back together again. So, first examine these things. How many of them are there? What other energy levels? And then maybe do something to try and find a way to impact the radiation of it, and then eventually develop some technology that might shield us from it. But that's not near term. But how long is it going to take for us to create the instruments for better observation? And then how long is it going to take us to create the technology to create a prototype to try and see if we can defend ourselves from it? And there is a probe that is the deepest diving probe into the sun's corona that we've ever done, called the Parker probe. And the Parker probe actually has panels that face towards the sun, and they're taking a beating from the sun, and the Parker probe will only last until there's a sufficiently large hole through those panels that the radiation from the sun as a beam makes it through to the electronics of the actual probe. And so if you want to see how would we defend ourselves against a high energy field, look at the Parker space probe. So
the other thing is that, like, defend our atmosphere and the loss of ozone, there is not much we can do.
not today.
Other than not today. So, but thinking about how to survive that, right now at this moment, we are advanced a lot of production into hydroponics, indoor planting, that would help to production of food. And the other problem that would be is the depletion of oxygen in the planet, because if we lose the phytoplankton in the ocean, those guys are the ones who actually keep the ocean, the oxygen that we breathe. So with the time, the oxygen would decay, and that will be problematic for all life on the planet. But I think to survive, if the hole or the loss of part of the atmosphere is not too big, the planet can survive. We can survive indoors. We have technology for that right now at this moment, and we are a lot of production of food. It's being done indoors, and maybe with a little bit of a larger flux of energy in the atmosphere, we can use the atmosphere to split water and have some of the oxygen for survival. Of course, it's not feasible for the whole planet in the case of the oceans and the life, but we might survive. We might survive with the technology that we have right now, but you never know in the future when we research more and learn more what will be necessary. We are ingenious species, so we might find a way.
So, the only thing we have to watch out for is something a very old black and white movie once taught us. What must we not have? We must not have a mine shaft gap. Don't you remember that?
Nope.
Nope.
George C.
What's
Scott?
that from? What movie?
Peter Sellers, George C. Scott.
Yeah, the one where he's falling down, holding on to the bomb when he goes down again. But what's it called?
That's the movie.
Yeah,
Dr. Strangelove.
Dr. Strangelove, or How I Learned to Love the Bomb.
Yippee, yippee. You remember he's having such a good time riding the bomb.
It was Wahoo.
Oh, I thought it was Yippee. Ah, man. All right. I got to rewatch that.
Yeah. If we have not advanced the technology to the point where we can put up some kind of electromagnetic shield to bend the electromagnetic radiation to protect the Earth, then our only other avenue is get inside a hole in the ground, make all of our own resources inside there, and maybe some number of years later come back out. But that won't be suitable for the whole planet. We'll have to have some kind of lottery. So
Yep.
Will be Eloy.
but the first thing we might wind up being the Eloy from the Time Machine.
Yeah.
But the first thing you have to do is, much like we've done with other impactors, is assess them, observe them. What is the threat? And we have not done that for electromagnetic radiation.
Monroe, what was the instrument that caught this weird white dwarf?
The two-mass survey, it was a broad infrared survey, and they were just cataloging stars, and they have to come across this star that looked like your typical white dwarf. And if they keep looking at them over time, they go to judge the parallax to see how far away they are. And from that, they noticed that it was pulsating. And then they did some additional observations in infrared and determined that it's headed towards us. But what they haven't done is the electromagnetic radiation analysis in other bands to see what kind of radiation is it putting out. What's its
So
spin
the
rate?
pulsation was in visible light or was radio?
It was in infrared.
Oh, okay, interesting.
This is not a neutron star, so don't expect radio. You might expect ultraviolet or X-ray. Probably not gamma, but you never know until you observe it.
If it's close enough, and whatever thing that's hot enough, whatever object that's hot enough produces all the wavelengths of the spectrum of light at the same time.
Yep.
So even a white dwarf, if it's close enough, will produce everything. But it's pulsating. It is interesting because normally when you have something that very bright that produces all the wavelengths, it's constant everywhere.
So before we actually get going on building our Dyson sphere or whatever is going to protect us, there's going to have to be a drastic change in world politics.
Yes.
Because, look at what we're not doing for global warming.
We already have the instruments we need to do the assessment. All we need to do is to have principal scientists file for use of the instruments for a particular project to say, I want to study this white dwarf with this particular instrument. And that's all they need to say. If they're going for their PhD, they could write their thesis on it. And if you do that over maybe 5 to 8 different wavelength instruments, you'll come away with the assessment you need. Now, a variable star, this isn't. This is a pulsating star, which means it has jets like a neutron star. And those jets are tilted towards us. So as this thing is rotating, we're getting sweeps of the polar jets. If it's a variable star, the star is actually swelling up, breaking down.
Yeah.
And it does that over days. Think of Algol. Algol is a variable star. And we've seen that for a long time. It's not going to do anything anytime soon to us. But something that is pulsating at less than 1 minute, but far more than 1 second, it's not tight enough, it's not spinning fast enough to have become a neutron star. There's not enough crunch to it. But it is a bit more than your typical white dwarf. So it has kind of the beam characteristics of a pulsar, but the beam is going to have a different composition, a different energy level, different flux, and have a different diameter.
How did you get to the information about this star? That's very interesting. I want to read about it.
Is it supposed to be top secret?
No, I don't know. What is it?
I monitor observations, and when they said, we have a star that looks like a white dwarf, and it's headed towards us, but we don't know exactly how fast because it's very much blue shifted and has a more intense magnetic field than your typical white dwarf. And I said, oh, That's interesting.
Intensely blue shifted, so the speed towards us is very fast.
Yes, but not as fast as they originally thought. Originally, they thought it was doing about 4,000 kilometers per second. And as it turns out, it's only 84 kilometers per second.
So why did you find that one?
I had to look it up. I had to look
Okay.
it out. You know, you start, if you can find the basic identifier, the WD identifier, you go to the SIMBAD catalog in France, and you look up the detail on it, and it will tell you whether catalogs it's in. And then you go to
Nice catch for you to look in the catalog and find that one. That was a nice catch.
No. I had the WD identifier from a news article from 2 years ago when they were questioning, okay, it's moving towards us. How fast? We've got 3 different opinions. Okay, that gave me the identifier, and I went, well, I'm going to go to SIMBAD and look this thing up. I looked it up and said, here's all the other catalogs it's in. The next thing I said was, of all the other catalogs it's in, what are the wavelengths they've observed it? What kind of instruments have they used? And they've only used infrared. Well, what about, you know, gamma and X-ray and UV and radio? And like, no other observatories have looked at it.
Okay. So it was an article. So the answer to my question, it was an article that you read 2 years ago.
I didn't read it 2 years ago. I read it like 3 weeks ago and saw it and said, I've got an identifier. I've got that WD identifier. And then I went to SIMBAD, looked it up, and then went to all the other catalogs that it's in and said, what is the observing of it? And all the observations were infrared. Then you've got to ask yourself, how do they know it had such a large magnetic field if they've only observed it in infrared? Well, you know what the answer to that is? SOFIA. SOFIA has computer processing routines. No, the processing routines are still. They can take infrared observations and come away with magnetic field flux lines. And that told them how deeply the light is bent in infrared by the magnetic field lines. So high magnetic field and slow pulse period in infrared. But what is the pulse period in other wavelengths? Because the beam under an intense magnetic field will actually not be straight, it'll be curved. Kind of like the emissions from the white dwarf that are coming out broadband actually get bent like they're going through a prism by the magnetic field. So, you know, you're going to get, you know, maybe the higher energy portions of the beam first, and then you'll later on get the visible and then the infrared and then the radio. So it'll be spectrally split out already. Just me connecting dots.
What was the place you read it? I want to read the article.
Well, let's see. If you go back, there you go.
Which one?
The first one, star moving towards solar system at 4,300 kilometers per second or a weird magnetic illusion. It's a YouTube video. And then I took from that, okay, I've got the WD number. Now I can come back and look at it and then compare it against, I'm not, you know, is this the only one they've ever found like that? Because it might be an instrument error. And then I found that this AR Scorpii is the same kind of thing. It's a white dwarf, and there's more than one of these, so it can't be just an instrument error. And then you can look up, it actually has an Expedia article, and you can look it up on SIMBAD. And then anything from the Gaia D3 that might be headed our way. There's a science paper on that, an abstract on it. And then the fact that it shows up only in infrared in SIMBAD. So I have a link off to the VizieR, which is an infrared catalog of observations. So they've actually observed it in infrared. And then I said, well, now we're going to talk about lining things up and getting things synchronized. So I had to understand the Earth characteristics, you know, its diameter, circumference, orbital velocity, and then the orbit around the sun and what that velocity is to see, you know, what would be a bad day for us? How would the cards line up against us? So
it was a nice catch. Nice catch. Very interesting star.
You know,
Because it's like in schools, even like when you do college, you know, I have basic knowledge, didn't continue all the studies, but you know,
I,
mostly you have, you know, those just the stars that you see in a cycle that you start in the beginning. There is no in
I,
between yet
yes, I
for the
wanted to have
basic
I wanted to
courses.
have enough information in the presentation and in the links that maybe if this thing gets posted on YouTube as a public video, maybe some white dwarf professional astronomer looks at it and goes, "Huh, I didn't know about this." And they're looking for like, what do I do with my next research paper? How do I get my next grant money? How do I get my
Yep.
next time on the KEC or whatever? Um,
Yes.
this could be a way of doing that, and that will create the, you know, the
The
desire to
buzz.
have observations for things that aren't just going to smack into us, but you know, things that are going to shine the light beam on us. Just me connecting dots. Okay, comments or questions? We're early.
Crickets?
I'm hearing crickets. Maybe everybody wants to say something after we turn the recording off.
Yeah, we're hiding it. Yeah.
Okay, so I'm going to stop recording.